calculated the values of S2 in a table. We went ahead to calculate the values of the design wind speed, which is site-specific to our assumed site. We also went ahead to calculate the dynamic wind pressure that was resulting from those design wind speeds. We also calculated the resulting force on the whole building. If you will just remember, on the whole building, on one face, the longer face, which is 35 meters, we calculated that. We went ahead to, again, divide that force per frame, so that then we would have the values that we would put in at those at the nodes of this frame as point loads courtesy of the wind. So this we did, and we agreed also that you would then go ahead and complete this table and also calculate the forces in the x direction, that direction. And I trust that you were able to do that. Maybe at the end of this session, we could have 1 or 2 groups showing us what they have done. I would also like you to start off on the sorry, on the ETABS modeling. Maybe we'll spend some bit of time, maybe 10 minutes or so, and just mention to you the modeling on ETABS. I hope that you are able to find this or any other software that you want to work with. Personally, I work a lot with ETABS, so I would find that easy to assist you in case of any challenge in the modeling. And in any case, this software, they more or less the same. If you once you know how to work with one software, for example, even STAAD.Pro, if you know the thought process of how STAAD.Pro works, then it's very easy to pick another software and work with. The other advantage that for example, a software like ETABS has is that there is a lot of tutorials on YouTube for it. So for any problem that you encounter, you just need to search for a tutorial, and most probably you find a solution. Somebody has had this problem, and they have found a solution, and they have made a small video for it. And it's not just tutorials from the creators of this software, but it's tutorials from engineers in practice. So they are really practical tutorials, and they solve some real problems that you would encounter. Now, today I want us to get started on earthquake loading. Just to remind ourselves what we are doing, let's go back to the content that we're supposed to cover. So we have mentioned a bit, we started with the design philosophy, and we talked about what in brief what used when we're designing high-rise buildings. Specifically, we didn't talk about high-rise structures, but buildings. And we have started a discussion on lateral loads. We've started a discussion on lateral loads. We have talked a bit about wind, and I want us to spend the next few lectures to talk about seismic loading. And as we do that, I'm requesting that now we start doing the modeling in the computer, so that then we can go ahead and talk about the analysis and how we would design a typical high-rise building. So we're trying to deal with all of them together as we go along. So today I want us to get started on earthquakes. The date. So today is what's the date today? 28th. September 2023. Okay, we want to talk earthquake loading. So I did mention in the in the other unit that basically an earthquake force is an inertia force. The earth is moving, the building does not know that the earth is moving, and therefore it wants to remain where it is. Okay, and we went ahead to say that the force that the building experiences is pretty similar to the force that you would experience when you are in a vehicle and it's going in a straight line, and then it does a curve, and you feel like your body wants to continue in a straight line. Okay, so this is the force that a building would feel, and the faster the earth moves, the bigger the force that the building feels. So to start us off, maybe we can write a small note. And I will seek to just move from what we had already discussed and put down as notes in the other unit. So I will add a few more notes here. Now, we did mention that there are few factors that do affect the force that a building would experience in an earthquake occurrence. We say the type of structure, etc. And in this unit, we will look slightly more into detail of these items. But generally, the way a building responds to earthquakes depends on the stiffness or flexibility of the building. Just as a general statement, let's put it down. The way a building an earthquake depends on the stiffness or flexibility of the building. Stiffness or flexibility of the building. Okay. Now, you know, it is easy to think that the stiffer a building is, the better it is for that building in an earthquake. But that is not absolutely true. For areas where they do very tall buildings and those buildings are prone to significant earthquakes, they actually design those buildings to be able to deform in an earthquake, to be more flexible, to be more ductile. Because in the building deforming, the energy that the earth imparts into the building by its motion gets absorbed, gets dissipated. Let me deviate a bit. I am told, I'm not a mechanical engineer, but I'm told the way cars are built or designed nowadays, they're designed such that they deform on impact. So the front deforms on impact. And in that deformation, the energy that would have otherwise been used to deform the human beings in the body a lot of it is dissipated by deforming the vehicle itself. So it's the same, it's a similar concept. If I may take you back to your secondary school physics, you remember that when you calculated the force of impact was dependent on two main variables. There was time of impact and there was velocity of the object that comes into impact. As you increase the time of impact, the force of impact reduces drastically. As you reduce the time of impact, the force of impact increases drastically. Let's even think about a more practical example, and we can even illustrate this here. Look, there's a wall, eh? There's a wall here. And there's a blockboard here. There's a blockboard that you can pin notices. So if I punch the wall, the time of impact is much smaller than if I punch the board. If I punch the board, the time of impact is bigger. So I feel less force. It's less painful to punch the board than to punch the wall. Because time of impact that takes as I punch the board is much longer. So the force that my hand feels is smaller. It is a similar concept that if the building is a bit more flexible, when the earth moves, then the building absorbs better the energy, and therefore it is a bit more desirable than if the building was absolutely rigid. It's a concept that you need to think about it. It's food for thought. So the stiffness or the flexibility of a building is important in calculating the earthquake force. Okay. So from what I've just said, we can write here that it is more desirable to have some ductility. It is more desirable to have some ductility in the building to allow absorption of earthquake forces, as the members of the building deform. Now, I want to take you back to your dynamics of structures. Okay. So if you can remember properly, when a system is excited, given an excitation force, it vibrates. And that vibration is a function of the mass of the system. You remember lumped masses, eh? So you'd have maybe a single mass or a multiple mass, multiple degrees of freedom. Okay. So it depends on the mass, and it depends on the stiffness of the springs that are supporting these masses from your dynamics of structures. Now, buildings tend to have a similar behavior, that when an excitation force, in this case an earthquake, shakes the building has got mass. It's got walls, concrete, everything. And the building also has some stiffness. The materials that we use to build the buildings and the elements of the building, the beams, columns, walls, etc., etc., they have some stiffness. So the buildings tend to, therefore, dance in some pattern. They tend to dance in some pattern. Okay? And that dancing is dependent on the mass of the building and the stiffness of the building. The mass of the building and the stiffness of the building. So we can talk of the period of vibration of a structure. I'm just doing an introduction, then later on, all these thoughts that we are sharing will become more clear as we delve into what the standards say about how we design for earthquakes. The period of vibration of a structure can be different when considering different directions in the layout of the building. Hello? I'm in class. Yes. In the layout of the building, due to the difference in stiffness of building, in different directions. If you try to push this building, this our hypothetical building, if you try to push it in that direction or in that direction, it's a lot easier to push it in that direction because it's slender that way and it's less stiff. It's more flexible that way than this way. So in an earthquake, a building like this would have a different vibration pattern from your dynamics of structures. Will have a different vibration pattern and by extension, different periods of vibration in one direction compared to the other direction. That's what that statement says. I'll write maybe one or two more, and then we will look at what the standards are saying. What this statement therefore means is that the earthquake force that a building experiences for the same magnitude of earthquake may vary in different directions. Of the building in plan, depending on the dimensions of the building, in those considered directions. Don't worry about these statements that I'm putting as foundational thoughts, because we will look at the numbers as we look at what some standards are saying, and this will become very clear. It's just a thought I want to throw to you, that because the earthquake force on a building depends on how stiff or flexible the building is. If you have a building that has got different stiffnesses in different directions, for the same magnitude of earthquake, a building can experience different magnitudes of earthquake force for different directions. For example, this building that we are looking at, the earthquake force that it will experience in that direction and in that direction will be different, because the stiffnesses are different, the periods of vibrations are different, and by extension, therefore, the force that the building will experience in the X and in the Y direction is different, just because the building is more stiffer in the X direction than in the Y direction. We'll look at these thoughts to a lot more detail. Now, there's a large array of standards that have been developed all over the world that deal with earthquake forces and how we can calculate them on buildings. There's a large array of design standards from different jurisdictions that give guidelines on how to take care of earthquake forces in buildings. There are some that are very old, there are some that are very new. My approach to discussing this subject is to pick an old standard, because the older standards are simpler. Like now that I have discussed or have introduced to you the subject of wind, for example, we used a very old and pretty simple standard. Now you can go and pick, for example, the BS 6399. If you pick it and try to read it, you will see a lot of similarity with the older standard, only that now it is a lot more refined. If you picked the Eurocode for wind loading, you will see a lot of similarity. The basic concepts are the same, but it's a lot more refined. It's got a lot more considerations, a lot more factors. So it's a lot easier now because you have the basics to follow up and understand the other standards as well. So I want to do a similar approach for this for this discussion on seismic loading. So straight away, allow me to open some standard and introduce it to you. Yeah, we have a lot of time. We're in good time. We should be able to. References, exports. Sorry.
Good morning. I have a question.
Yes.
You've talked of the stiffness of the building in different directions, and
yes,
it got me thinking. Some buildings don't have a square column. They have columns that are maybe rectangular, and that column itself will be stiffer in one direction than the other. So when
Correct.
you construct such buildings, what inspires or what informs the arrangement of those columns?
So I think that's a very good question. Who was asking? Please, if I could know the name. Hello.
Hello, pardon?
I wanted to know who was asking. So this is Mutero. That's an excellent question, and in this course we will answer that question. We will answer that question when once we understand how we can quantify the earthquake force. We will come to say, how do we stiffen the building? That's when we will now talk about the shear walls. We'll talk about how we arrange the columns to achieve the most efficient use of them in a building against lateral forces. So that's a really good question. We will answer it in this course. In this course, please, if you'll allow us, later on we will absolutely be able to. Before we finish this course, you will be very clear how you would orient your column. But I don't want to go into that now. I want us to go step by step so that we don't have gaps. We don't skip and then we have gaps. Okay, sorry, just a small itch with my thing here. Sorry, I'm using my. Okay, great. Sorry about that. So I was at the point of opening for us. Yes. So I am sharing with you here an earthquake code that was written for Kenya some years back, and I will tell you the stories of this code as we go along. Let me just clean it up a bit because I've used it before with some other groups. We'll go cleaning it up as we proceed, but we just remove some of this on the first pages. So now, many other jurisdictions, our neighbors might not have standards to calculate earthquake forces for their countries, but we have the blessing that many years ago, some scientists put together a standard to guide us on how to design for earthquakes in Kenya. And I think this is one of the simplest standards that you will find for earthquakes, and it's a good thing that it's written for us in this country, so it's very, very applicable here. Of course, it is limited. It has limits, and I will highlight those limits as we go along. But this is available. So I want us to look at how we can deal with, first, calculate earthquake forces and how we provide for them by first referring to this standard. And as we go along, I'll keep telling you what the difference is between this standard and the newer standards like the Eurocode, like the American standard for earthquake calculations, like the Unified Building Code, International Building Code. I will mention a few things as we go along, what the difference is between this standard and those standards. I will also mention as we go along what are the similarities, which is basically forms the foundational theories of how earthquake forces are calculated in buildings the world over. Now, before we get started, I also want to mention that generally, design for earthquake forces is a very complex problem. Just like the analysis for wind on buildings also, we say it's a very complex problem. So we do not have all the answers for earthquakes, just like they will not have all the answers for wind. There's a lot of researchers that are doing still research on how buildings behave in earthquakes, on how earthquake forces are generated in buildings. This is an area that is still under a lot of study, and there's a lot of information that us as engineers in the world we do not know. But we also have some level of understanding which has been accepted and has been in use for many years. For example, you notice that this standard is how old now? We are 2013 minus 1973. This standard is 40 years old. And at that time, there was a fairly good understanding of earthquakes to warrant or to mandate some experts in this country to write this standard. So I will take you through the thoughts of this standard. It's a small standard. It's very, very interesting. And then we will see how we proceed. So the work of this standard was based on the work that a certain professor of geology did at the University of Nairobi. This was a professor of geology, Professor I.S. Lupekin. He was a professor of geology at the University of Nairobi, Chiromo campus. So he did a lot of work on seismic quantification, seismic data collection, seismic records, and things like that. And it is based on his work that this standard was written. So part of that work, I found a document that Professor Lupekin wrote, and you as well. I thought it's an interesting document. So this is a document that Professor Lupekin prepared those years. So this gentleman, he recorded a catalog of felt earthquakes in Kenya between 1892 and 1969. So he recorded all the earthquakes that had been recorded or had been felt and that were on record in Kenya that happened between 1892 and 1969. So he produced this document, and it was from this document which he produced of the earthquakes up to 1969 that this standard then was written. Without much ado, let me show you a sample of what this document contains. So there's some preliminary thoughts that he put there. Then he went ahead. So I'll share this document with you so that you can have it in your records. If you're interested, you can read bits of it. It's not a big document. It's only 65 pages. But it's really interesting to know where the thoughts that we'll be sharing came from. So this is the catalog. This is how he cataloged the earthquakes. So for example, if you look at this entry here, it says in 1905, November 30th, this was the Voi district, Upper Coast. Sudden shock followed by soon after by a tremor which lasted for a few seconds. Okay, so that is the description of the earthquake that happened, and he also gave the reference where he got this information from. So this, I think it was a form of newspaper or something, East African something, so which was published on 9th December 1905. So if you went to the archives and if they have this document, you can actually go pick it and verify that indeed this information was recorded there. So then, so going down, so he recorded all these earthquakes. In 1919, for example, between Kedong and Nakuru, there were frequent small quakes, and he gives the reference. This is a document that was written by a fellow called Gregory in 1921. Okay, and so on and so forth. So it's really an interesting way and a lot of work that this gentleman did, and we are grateful for him. So 1922, March 15th, slight earthquake felt in Masara, Madari area in the early hours of the morning. Rumbling noise followed by a series of tremors. Dogs barked. You know, that's interesting. Dogs barked and then became subdued. Birds stopped singing and flying for half an hour. And glassware was broken. Now, please take note of this, damage to buildings. Damage to buildings. Shortly, I will talk about it. And a swamp was drained, courtesy of that earthquake. And he says where he got this information from is this publication, EAS of 16th March 1922. Let's look at one more. So 24th June, 29th June 1924, in Kitale, slight tremor at 10:45 a.m., followed by a stronger tremor at 9:25 p.m. So one in the mid-morning, one in the night. Tremor at Glanville caused by swaying of a bed and by the geology of what caused this tremor, and then his information is. Okay, so this is the catalog that this gentleman prepared, and from this catalog, then he grouped the intensities of the earthquakes. From this catalog, he grouped the intensities of the earthquakes. That's what these numbers are, and I will show you shortly what they actually mean. That's what these numbers are: 3, 5, 3, 7, 3. These numbers, they're actually his categorization of the earthquakes. Okay, so that's what I want to show you now. So if we go back up this way, he came up with this scale. He came up with this scale, which varies from level 5 to level 9. Varies from level 5 to level 9. 5 to 9. So what Professor Lupekin did, he defined the intensities of the earthquakes in terms of the building that the damage that those earthquakes did on the buildings. I'll repeat. Maybe I should even put it down here. Professor Lupekin defined the intensities of the earthquakes in terms of the damage that those earthquakes did on buildings. The intensities of the earthquakes in terms of the damage that those earthquakes did on the buildings. Okay, this is important, ladies and gentlemen, because this is one place where this standard deviates from the more recent standards, allow me to call them modern standards. This classification, where this standard classifies the intensity of the earthquake based on how much damage that earthquake does on a building, this classification deviates from what more modern standards, or from how more modern standards define earthquakes. So let's look at how he defines these intensities. So if you look at category 5, it says a few instances of cracked plaster. Then category 6 says a few instances of falling plaster or damaged chimneys. Damage is slight. Then category 7, damage is negligible in buildings of good design and construction. Slight to moderate in well-built ordinary structures and considerable in poorly built or badly designed structures. Some chimneys are broken, and it continues in intensity as you go up. Now, the problem with this classification is that it is not precise. For example, I'll ask a question. How do you define a well-built ordinary structure? It's a grayish definition. It's not precise. Okay, so that's one of the major shortcomings of this standard, that it did not precisely define an earthquake intensity, but it defined the earthquake intensity in terms of the damage to a building. And the quality of a building is such a huge variable that we cannot use damage to a building to accurately measure an earthquake. So what the newer standards have done is that they have now defined the intensities of earthquakes by using the peak ground acceleration that the earthquake causes. So more recent standards use the peak ground acceleration. So how fast does the ground accelerate? And that's a more precise measure to use of an earthquake. So this is one place that is important to note. Now, from this categorization, Professor Lupekin went ahead, and at the end of this document with intensities of earthquakes, he drew a map of earthquake intensities for Kenya. He drew a map of earthquake intensities for Kenya based on that classification that he did. Okay, so he says there's a zone 5, zone 6, zone 7. For example, Nairobi, maybe we might not be able to see this. This is an old scanned document. Let me make it a bit bigger. We see if we can find Nairobi. Yes, Nairobi is right here. Let me use a lighter color. Nairobi is right there. So it's zone 7. Zone 7. Nairobi is zone 7. Okay. And like that. So now, this is how this standard defines earthquake intensities from a structural engineer's perspective. The newer standards, as I've mentioned, they have used the peak ground acceleration as the basic way of defining how strong an earthquake is. It is a similar thought like when we were discussing the wind, when we talked about the basic wind speed. We talk about the basic wind speed. So in earthquakes nowadays, and those peak ground accelerations, they vary from one region to another. Later on, I will show you a map of Kenya that has got now that is mapped this way for peak ground accelerations, and you see that that map is very similar to this map. That map for peak ground accelerations for Kenya is very similar to what this professor 40 years ago, or actually more than 40 years ago, he suggested in his in this document where he did a catalog of earthquakes that occurred in Kenya those days. So with that thought, therefore, we can say with authority that indeed this gentleman, his work was accurate in that the zoning qualitatively is agreeable to the more modern zoning, which says that generally the places, for example, the area where you have the lowest zoning, also in the modern maps, you find similar, those areas have got the lowest zonings. Of course, we know that along the Great Rift Valley, this is where we have the highest intensity of the frequency and intensity of earthquakes. Okay, and you notice that in this document, in this map, this gentleman suggested that this is where we would have zone 8 and 9, where we have the most intense earthquakes. You notice that zone just follows the Great Rift Valley, of course, because of the tectonic plate movements that are known from your geography, are known to be frequent along the Great Rift Valley. So with that introduction to where the Kenyan standard for earthquakes came from, now I want to go back to this standard and to see what this standard says. And you'll see a lot of information on this standard that was lifted directly from this document, including this map. This Kenyan map for earthquakes, if you come to this Kenyan standard for earthquakes, at the end, they put that map there. That exact map, they just lifted it and put it into the standard. Okay. So now let's look at this. Let's look at this standard a bit before we wind up. So there's a committee of whoever was there at that time, chief structural engineer, chief architect, you know, like that. As a result of much research of all records and collection of new data, the sum total of present knowledge of earthquake data relating to Kenya has been published in 1971 as a catalogue of felt earthquake intensities, which I've just shown you. So they say have been because it was pretty recent that time when they were doing this. 82 to 69, I've shown you this catalogue, and the work was done, of course, by Professor I.S. Lupekin of Geology Department, University of Nairobi. Produced in this code is a seismic zoning map showing maximum observed intensities and dividing the whole country into zones of various likely degrees of intensity. Now, please watch. This is an important. Thought. Is actually probability. Likely is probability. If I may deviate a bit from what we're discussing, you will notice for all structural engineering applications, the loads that we actually apply on structures, they're loads that are based on probability. They are loads that are based on probability. So earthquake forces also are calculated based on probability. So we're saying Nairobi has been feeling this kind of earthquake consistently for many years. So what is the probability that this kind of earthquake of this intensity will occur in Nairobi? Okay. So this is the thought of loading. All loads, including the live loads that we put on buildings, the wind loads, the loads we put on bridges, they're all based on probability. We're saying what kind of vehicles pass here, what is their weight, so what is the probability that this kind of loading will be experienced on the bridge. So then we work it out. It's a statistics thing. Possible effects on buildings, which I've just highlighted to you as the basis for this categorization. Possible effects on buildings. Various zones are as follows. So you, again, if you can remember shortly, we were looking at this categorization that was pulled from this standard. It's exactly word for word. They just lifted it and put it here. So basically, one could say that the father of that our standard is this gentleman called Lupikin. Okay, so that was lifted word for word and put there. Up to that point, ladies and gentlemen, any question? Any question? Any comment? Now, if somebody has a question, just switch on your mic and talk. I'm not able to see this other window. I'm on a different window. Just switch on your mic and talk. Okay. So now, in a previous session, we did say that when we were talking about wind, if you can remember the factor S3, we said that it's a factor that considers the importance of a building. Those who were in class recently for that session will remember. And we said when we talk about earthquakes, we will dig into this factor a lot. We will dig now deeper. So there are several considerations that affect how much intensity of earthquake we should allow in a building or on a building. So the first one is how important that building is. The first one is how important that building is. And that's the first categorization that we need to think about. Classification of building, usage, and value. So two things. How are we using this building for? What are we using this building for? And what's the value of this building? So this standard proposes five categories for how important a building is in terms of how we intend to use it and how important it is. Let's just look at these categories, maybe one or two. So Class A is buildings for public assembly and use. So government buildings, courts, police stations, halls, lecture theaters, cinemas, sit stadia, hotels, school buildings, churches, all that is put as category Class A. If you look at these examples that have been listed under category A, they are buildings that either they deal with the security of the country, they deal with the governance of the country, they deal with large populations, they deal with emergency services, they deal with transport. Okay, so these buildings, we would generally want to ensure that nothing happens to them. Then it's also important to note that this list is not intended to be comprehensive. So you, as the designer, you're free to add other buildings that you consider as important as this group of buildings. You can put them into this into this group. The next category is large buildings for multiple occupation, but not public use. So office blocks, restaurants, buildings up to 3 stories, shops, flats, they fall under category B. Sorry, just a moment. Good morning. Sorry, I was asking for a few more minutes to. So, ladies and gentlemen, at this point, let me ask a question for you for us to just discuss as we come to the end of this session. At that time, we didn't have malls very much. That time, we did not have malls very much. Okay, but now we have malls. Would you put malls here or here? Where would you put malls? Because for sure, this standard says shops should be category B, in your own judgment. And now that you know what this categorization looks at, where would you put malls? Any suggestion? We will close this session in the next 5 minutes. Charlene, please go ahead.
Class A.
You put that as A. Why?
Population, it has a lot of people.
Correct. Correct. You know, we have very many people coming into these places, and just because of that, if failure was to occur, then the loss would be to human life would be astronomical. So definitely, then this would fall under category A. Let's go down the list a little bit further. Then there's category C, which is building structures and services for industry. So factories, power supply, etc., etc. And dams is put as category C. Again, I want to throw it to you, ladies and gentlemen. If you were designing a dam today, where would you put it? Category 1, category 2, category 3, or category 4 and onwards? Where would you put dams? Food for thought, ladies and gentlemen. It's open discussion. I mean, sorry. Dams. Where would you put a dam? Yes, Charlene. So let's hear Brevis.
I'll put it on category C, class C.
You put it as class C. Reason?
See, it's a building, it's a large structure for services and industries.
Okay, so let's engage a bit, Kwemoi.
Yes.
A few years ago, there's a dam that collapsed. It's a small dam. It was a private dam, Solai Dam. Did you hear the story of Solai Dam?
Yes.
Okay, so I want you guys to go and read the stories about Solai Dam and the kind of loss that occurred because a relatively small private dam failed, collapsed. And then I want you to push this thought further and go to YouTube and search the stories of the dams that collapsed in the world. In some collapses, entire cities were wiped out. Like there's one dam, I can't remember the name. It failed at night. In the morning, during the day, the previous day, there was a complete city on the river valley below the dam. Complete city, complete town. In the morning, there was nothing. The dam collapsed in the night and wiped out everything. Vehicles, roads, buildings, people, everything became a clean, plain river valley just because the dam failed. With the information we have now, and I want you to go to YouTube and look at these stories because they're very interesting and they're relevant for our discussions. Now that we know the kind of devastation, even a small dam like Solai Dam, I want you to check out Solai Dam. I would definitely not put this one here. I would put it here. Why? Because we are looking at the importance and the kind of loss that would happen in case that structure was to fail. And of course, as to conclude this this session, of course, the last category is domestic buildings in rural areas. You know, if you're building your bungalow, maisonette, or shago, then this rightfully can be categorized as class E. You know, if an earthquake was to happen and a wall was to collapse, it would not make even local news. Okay, importance of the building. Ladies and gentlemen, I want to stop here for today. We will continue with these thoughts in the next session. Now, I want to allow, if somebody has a question or a comment, we could hear them out before we conclude this session. Yes, this is Gilbert. Gilbert, please proceed. Hello, Gilbert. See if he's written anything here. Gilbert says, please explain the effects of using tendons on structural stiffness of a multi-story building when controlling the seismic loading. He says he has mic issues. Okay, so I think this question might be dangerous if we tried to answer it now. And I will just shed some bit of light on what tendons are used for. Tendons are used for pre-stressed concrete instead of reinforcement. Tendons, compared to the reinforcement that we use, they are very high tensile steel. So they are much less ductile. Tendons would not be used for compression reinforcement, for compression elements like columns. And I'm just throwing general statements which might be dangerous in confusing you. I would keep off this subject for now. Maybe Gilbert, as we wind up this topic, as we wind up this topic on earthquakes and on the design, once you have done the design of this building, please remind us to revisit this one, because at that point we will be able to have a more meaningful discussion between myself and yourselves. I wouldn't want to dwell into it too much at this point, but generally we wouldn't use tendons on compression reinforcements. So basically, we wouldn't use that on columns, maybe on walls, but I'm still trying to think of what would justify the use of pre-stressing on walls that are carrying predominantly compression. It might not be a very good idea, I don't know, but I'm leaving it open. Maybe you came across something that is interesting, we will also hear from you. But first, let us just get the basics right, and then we will revisit. We can revisit this. So please keep this question. We'll revisit it as we wind up this the discussions in this course. Then maybe we'll be able to make a little bit more sense. Yes, Elvis, your hand is up. Please proceed. I will answer your question. The answer is definitely yes, but you are misquoting me. Just repeat what you just said so that I tell you where you're misquoting. You didn't understand what I said. That is correct. There's something else you've said that was not correct. The stiffness is correct. There's something else you said that is not correct. Now it is going out of my mind. The stiffness of building affects how much force eventually the building feels. Absolutely, you will find in real life the stiffness of the building, every floor is likely to be different. Because the stiffness of the building is dependent on the size of the columns, the location of the columns, the orientation of the columns, whether you have walls, masonry, or reinforced concrete, whether they're shear walls, whether they're just partition walls. All that contributes to the stiffness of a particular story. So definitely the stiffnesses keep varying as you change from one floor to the other. And a lot of times, because we tend to reduce the size of the columns as you go up, the stiffness of the building tends to reduce as you go up per floor level. So this is a common, is a normal thing when you design buildings. Okay. Any other question? Any other thought that somebody might want to share with us? Gilbert, utukumbushe hii story ya tendons tuichukue tena hapo mbele tukimaliza hii as we winding up this course. Okay, ladies and gentlemen, thank you very much. Have a good morning. We meet again in the next session. I think we don't have time to look at at this work. I want you to do this. I want you to look at this software and make an attempt to model this building. If you try it, then you learn. If you don't try, you don't learn. If you have challenges, we will deal with those challenges, I think, in the next session. Then also, there is that assignment I gave. Please complete those forces because we will need them to calculate and put them into this building. So thank you and have a good morning.